does it know we're recording? There we go. So welcome everyone. It's Wednesday, October 6th, Nobel Prize Day. Unusually the chemistry Nobel for chemists, because no other Nobel Prizes matter. So unusually the chemistry Nobel Prize went to a bunch of chemists. Normally it goes to a bunch of biologists doing molecular biology who've applied chemistry. But this year it went to a bunch of chemists doing organocatalysis, which we are not really going to talk about at all in this course. And I've been sort of thinking about, hey, can I work it in here somehow? And the answer is no. No, I can't. It's mostly using reactivity patterns that we haven't spent and are not going to spend any time talking about. But that's cool. They are both absolute assholes, and so my excitement for having it awarded to a bunch of chemists is tempered by the excitement of who it was awarded to. Anyways, last class we were talking about rings, and I actually got a good question here, very formal email, asking if I could go over exactly how to draw these effing chairs and how to do it. So there are two ways you can draw a chair. Notice I'm drawing individual lines. There is that one, and there is that one. It really depends if you're looking at it a little bit from the left or looking at it a little bit from the right. I'm gonna turn on my camera because politeness. Teaching from home today because I want to actually get something done, and it doesn't work so well in my office. So the first thing we need to do is what you can see. What I want to point out is if you take a look at any of these bonds, you can sort of imagine that's kind of like two arrows pointing this way. Like this line here is pointing down. And this line here is pointing down as well towards this carbon. So things coming towards it, they're down. That means that the axial at that position must be down. You can follow that rule for every single one of the carbons. And the reason for this is because this is just the way tetrahedra work. All these carbons are sp3 hybridized. All these carbons are tetrahedra. That means you need 109.5 degrees between each of the bonds and every other bond. And if your axial at that position is up, even if we're just looking at this, this is clearly under 90 degrees. Just the angle between the blue and the red. And under 90 degrees is not 109.5. So the axial cannot be up at that position. The axial must be down. And axials always interchange. If the axial is down at one carbon, on both adjacent carbons, it's the other way. And again, you can get that way by saying either, okay, because it's down there, it has to be up here, or by following the rules of the arrow. Like you can sort of see it, this is kind of an arrow pointing up. And here we have another arrow pointing down, arrow pointing up, arrow pointing down. And I'm kind of breaking the bond by making it look like it's going behind the one in front to give it some three-dimensionality. Okay, those are your axials. It's the same rule if you draw the other chair. Notice my axials are all vertical. I'm not messing around with putting them at angles. They are vertical. I don't know any other way to say vertical. They are axial. What I mean here is this. What I mean with the so if you're not seeing the arrow, ignore what I'm saying. But what I'm saying is these two bonds in the chair kind of make an arrow. Show it on the other one. These two bonds here kind of make an arrow. It's pointing up. The axial is up when they hit that carbon. Does that make sense, Alyssa? I was actually pretty proud when I saw this thing because I never thought of it this way before. I thought, man, I got a new way to explain this. And I got really excited about this. But if it's not making any sense, then it's absolutely freaking useless. Okay, but it made sense here. You like this way. Okay, if it helps, we should be talking about rings We're going to talk about some bicyclic rings today. So today is Wednesday, the 10th of October, and we should be talking about chairs, boats, and other conformations and Newman projections. And we will be talking about chairs, boats, and other conformations and Newman projections. On Friday, we will start talking about chirality. Yeah, I think lecture 9, 10, I don't precisely know. It's in the syllabus. But we're on track, and we're staying on track, and this is kind of a minor miracle. Okay, so all the axials are axial. Now, I think the fair question I get from people is, how do I draw these effing equatorials? And again, if you don't see this, I'm of two levels of sympathy. My level of sympathy, if you haven't tried to build a model of this with your model kit yet, is Tiny Violin. If you have tried to build a model of this with your model kit, and you've then tried to draw it, and you've looked at the drawings and tried to match things on, and you still can't get it, then I have a lot of sympathy, and I'm happy to go through that. But I think what I'm trying to say here is you just spent money on a model kit. This is why you spent money on a model kit. Use your model kit. Like, the box doesn't give you knowledge by osmosis by sitting there on your desk. I wish it did. It would be so much better if we could learn by just like having stuff of knowledge around us. But it doesn't work that way. So the equatorial, as I said last class, needs to be parallel. Here's this equatorial. It needs to be parallel. I haven't drawn quite parallel. I'll be better. To the bonds in the chair, and I don't know why I just deleted it. To the bonds in the chair that are not attached to that carbon. Okay, there are 3 sets of parallel lines in that chair. Plus the axials. We're going to ignore the axials. 2 of them are attached to that carbon. The third one over here and over here are not attached to this carbon. This bond should be parallel to those 2. Okay, just because it's parallel, why can't I draw it like this? That's parallel. Well, it's roughly parallel. Let's draw it more better. You're going to say, well, that's parallel to those 2 too. Yeah, it is. That is really not a tetrahedron by any stretch of the imagination. It's kind of like poking back into the core. You can sort of think of it as you got sort of the 3 feet of the tetrahedra here, and the 4th like crown of the tetrahedron needs to be pointing away from them. So your equatorials are always pointing away, however they can, away from the center of the chair. You can actually, if you build a model of this, again, build model, you'll notice that your equatorial bonds always kind of extend out from the centroid of the chair. Like if you had an imaginary particle at the middle of the chair, all the equatorials would be radiating away from it. So your equatorials are always pointing away from the middle of the chair. So for that carbon, it's there. For this carbon, it's there. For this carbon, it's there. And then there. In each case, we are drawing a new parallel line that is parallel to the set of parallel lines that do not interact with that carbon, or that carbon, or that carbon, or that carbon. The ones at the front and the back are the ones that are tricky. I agree, it's not intuitive that and delete the page, and that are pointing away from the middle of the chair. But if you build the model, hopefully you can see it. And again, if you haven't seen this in 3D with a 3D image here, I am drawing a 3D representation in 2D, and it makes no sense. And there's nothing else I can do. I can't draw in 3D. The textbook does have some rotation chemware and things built into it, like a few animations and stuff you can play with, where they do play at this. And you're going to be using Spartan, and in some of your labs, you're going to be talking about some of this stuff too. So the labs do tie in with the things we're talking about here, which is nice. But until you see this in 3D, it's really hard to take this 2D representation and go, yeah, I see exactly how that's all 3-dimensional. So again, I so strongly recommend you get out your model kit and try it out. On the other chair, the bonds would look like this. Not quite parallel. I'm not getting out a protractor to make sure they're parallel. I'm also not getting out a protractor to make sure they're absolutely straight and all the same length or anything. I don't care. As long as they're like within small amount of error of each other, it's good. These are the two chairs. That's all there is. There is no other way to draw these. There are only two chairs. There are only ever two chairs. If you try and flip them upside down or rotate them or do anything, you'll get one of these two. There's no way around this. So these are the angles you should be drawing. If you draw any other angles, you're wrong. And like I can actually, again, not a lot of like really strict rules in this course. This is one of them. These are the only angles possible. So these are the chairs. We can do this thing with boats as well. There are two boats. We like things with two. Two is an easy number. It's less than 8, so I can count to it. And again, what we see here is we don't really get axial and equatorial as well. A little bit harder to draw all these. But these are all roughly tetrahedron. I'm probably exaggerating that, the flagpole ones. They're all precise tetrahedrons, just the drawing tends to be kind of difficult. And again, these are the only two boats there are. Like any given molecule, any given chair actually has 6 different boats, but you can only draw them in this way. You just move the atoms all the way around. And if you don't know what I mean by 6 different boats, in the chair, everything is equivalent. All the atoms are equivalent. In a boat, not everything is equivalent. These 4 atoms are the same, but these 2 are different. And again, I recommend you get out your model kit and play with it. This is the best way to draw a chair. Or this. Use whichever one you find easier. I draw them like the one on the left because that's the standard way to draw sugars, and I draw lots of sugars. But choose either. Thanks, Alyssa. It really does. Otherwise, what you're trying to do is go like, how is this 3D? What I'm drawing is 3-dimensional drawings in 2 dimensions, and if you're not used to doing that, this is really, 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 really hard. I'm also a really shitty drawer. And I don't have time to like make these works of art. So please, please, please get out your model kits. I can't emphasize that strongly enough. Student to water. You can drink if you like, but that's basically how you need to draw these things. And I can say that. Okay, what I want to talk about for this then is, well, I'm going to wonder, is there any other questions about chairs and boats about the drawing here before I move on? Well, we need to draw boats. I'm thinking. Yes, but not. But probably in the form of, if you notice where I had it, I had these chair in one of the lectures. I was showing how a chair flips. The chair flips from a chair to a half chair to a boat to a half chair to another chair. You might need to be able to draw something like that, and for that you need to sketch out a boat. Would you need to do like a lot of analysis on the stability of the boats? No. Okay, these are great questions. So Alyssa and Hannah, I am going to do you guys together, your questions together. So Hannah asked, if we go from a ring formation to the chair boat, does it matter how you number the carbons? The answer is no. No, it does not. Okay, what we're going to do is we're going to do a double Newman. And a double Newman is, well, it's two Newmans, I guess. Okay. Here's a ring, and let's say I ask you, please do two things. Let's draw this in the most stable chair conformation, and then also draw the Newman projection of that chair conformation, looking down this bond and this bond. The double Newman projection. So draw me the most stable chair, draw me the double Newman. So Hannah's question said, did it matter how I number the carbons? No, it doesn't. If I'm trying to name the compound, does it matter how I number the carbons? Yes, yes it does. But I'm not trying to name this compound. I am just trying to draw it. And so if I'm just trying to draw it, then what I care about is, well, drawing it. And so why I'm numbering the carbons, you don't even need to number the carbons. But I'm numbering them so I make sure that I don't accidentally go from going clockwise to counterclockwise. I don't accidentally start drawing the enantiomer. We're going to start talking about that next class and why that's bad, because you would lose marks. It's bad because you would lose marks. So numbering keeps my head straight, but you don't need to do it, and it doesn't matter which order you do it in. Okay, so I'm going to give everyone a few minutes to try and draw the chairs. And to figure out which one's more stable, you need to draw both. I need to draw both. I can't do it by inspection. Glasses are filthy. I don't know how glasses get so dirty. It's not like you touch them or anything. It just collects smudge over time. Oh, the upside down A's are eyes. Eyes. So we're looking down those bonds. Eyes on those bonds. That's how we're going to draw our Newman. Yeah, glasses are the worst, but every time I think about getting like laser surgery and shit, I get scared because I'm a coward and I don't like pain and blood and that kind of stuff, which is why I had zero interest in going on to medical school. It's so much more fun to make drugs because you can like save lots of lives instead of doing it like one life at a time. And then, you know, people don't die on my watch. This is a real improvement in my quality of life. So if we need to draw a chair, I'm just going to draw a chair. I'm going to put my chair together. And it's like, okay, I drew a chair. Success. At least you got a half a mark there on a 3-mark question or whatever. Start numbering the atoms. I am arbitrarily numbering the atoms. Apparently, I like numbering the top right-hand 1, 1 first because I think I've done it a bunch of times. I just sketch them in here. Okay, so I just need to make sure that I keep my ups up and my downs down. Carbon 1 has an isopropyl group. The isopropyl group is coming out of the plane towards me. The up position at carbon 1 is axial. Again, that arrow thingy. The arrow thingy is pointing up, and you don't get more up than pointing straight up. Just like you don't get more down than pointing straight down, which is what's happening to the fluorine at carbon 2. Then carbon 4 has got an ethyl group. The down position, if you need to do this because it helps you, the down position is a hydrogen. It's not indicated, but it must be down because the other one's up and it's a tetrahedron. And every tetrahedra has 2 lines in the plane, one above, one below. That's just how tetrahedra work. There is no other way. Notice I'm not drawing anything inside the V, because then it wouldn't be a tetrahedron because the angle would be less than 109.5. So if one's up, the other has to be down. It just has to be. There's no other opportunity. We'd be really screwed if carbons made 5 bonds because everything would get so much more complicated. There'd be so many different ways that things could happen. So we should all be thankful that we live in a world where carbon only makes 4 bonds because it makes our chemistry so much easier. We could live like in a phosphorus-based world where everything could make 5 single bonds and just no. I might have become a biologist then. Okay, and then so on carbon 5, we have a methyl group up and we have a fluorine in a down position. Again, the up is axial, the down is the one that isn't up. Yeah, I think a phosphorus-based life or me becoming a biologist. They both sound horrible to me, Lauren. Okay, so hopefully you drew this chair. If you didn't, now it doesn't matter if you rotated it. It doesn't matter if your carbon 1 is down here where I have carbon 3. Or your carbon 1 is where I have carbon 5. Doesn't matter. Or your carbon 1 is where I have carbon 2. Those are all just different views. We can rotate stuff. You're good. This isn't, you could have drawn this differently, it would still be right. But if you've drawn it in one of your chairs, you should have the isopropyl axial up, the fluorine axial down, the methyl axial up, and the ethyl and the fluorine equatorial. This then ring flips. That is an equilibrium arrow. So we've seen resonance arrows. We've seen reaction arrows. This is an equilibrium arrow. It means it goes back and forwards and literally goes back and forwards like molecules go from one to the other. Resonance, the molecule is all the same thing. We're just mapping it differently, visualizing it differently. Equilibrium means this is actually changing. And you can use equilibrium for chemistry. We saw that with the acid and bases. No chemistry is happening during the ring flip. We're not breaking any bonds, but stuff is moving, and that is an equilibrium. So if we do that, and I said, hey, my little trick, I'm just going to slide everybody over 1 atom. I had to put like real thought the first time that I did this into where I should write the numbers so they don't get in the way of everything else. So if we do that, carbon 1, now the up position is equatorial. Carbon 2, the down position is equatorial. Carbon 3 doesn't have anything on it. Carbon 4 has an up ethyl. The up position on carbon 4 is now axial. Carbon 5, the up position is now equatorial for the methyl group, and the down position is now axial. You never need to draw the hydrogens in a chair. You don't need to label the methyl group either. You can just draw a stick. See, I've just drawn a stick here. So yeah, phosphorus-based life would be awful. You don't need to put the hydrogens in. If you put them in, it is not wrong. If you put in 1 or 2, it is not wrong. If you draw a stick and you meant it to be a hydrogen and you did not write hydrogen at the end, that is wrong because you're saying it's a methyl group. But if when you're initially drawing these, you want to put in all the hydrogens to keep yourself sane, go nuts. When you're writing an exam, you're not going to want to do that because it takes too much time. Yeah, so Madison asked, what if they pointed this way instead to do that? That is exactly the same thing. Either one of those is perfectly correct. They're exactly the same thing. What we're worried here is not what this bond is doing. Any other bond is doing. I have, oh shit. Nah. I do this occasionally and I can't figure out how to undo. I don't have a keyboard. Okay, plugging this back in for a second. There we go. Okay, I think I right-clicked, but I don't know how to right-click without a. Oh, maybe I have to hold. Okay, I'll figure this out someday. So what you should have drawn at this point is you should have these two chairs. And again, you could have them rotated. That would be fine. Like this is the same thing as if I had drawn. Not that bond angle is going to get ugly fast. I had drawn that and I put the ethyl group over here, methyl group. No, see, that's not the same thing because now I've done a rotation. Those two molecules are the same thing. Either one would have been perfectly correct. Just it's arbitrary where I start 1, 2, 3, 4, 5, 6. They're identical. So you don't need to draw both. You get full marks for either. Okay, but now the question became, so the question was, which one of these is more stable? And draw that as the Newman projection. Absolutely, Katie. I think we discussed that a few lectures ago. Yeah, filled in is up, dashed is down. Hannah, exactly. So when you chair flip, everything that was axial has become equatorial. Everything that was equatorial has become axial. That is inherent in every chair flip. But everything that was up stayed up, and everything that was down stayed down. It's just all your axials became equatorial and all your equatorials became axial. So if we look at these, we need to determine which of these is the more stable one. So this guy on the left here, we can count. It's got 3 equatorial, 2 axial. And over here we have 3 axial, 2 equatorial. So that's worth keeping track of. This one is looking better because it has fewer axials. Fewer axials is always good. Again, build your model, take a look. The problem with axial, draw it over here. Let's say you had an isopropyl group there. It doesn't really matter what is at the other axial positions. It can be hydrogens, the smallest things possible. But these are bumping into each other. This means steric clash. Like if you build a model and try and rotate a isopropyl, you'll go, wow, that's getting close. Because an isopropyl, right, is a carbon and then a CH3. Add in all the atoms. And what you'll notice is that those CH3s are trying to occupy the same physical space as these hydrogens. Even a simple CH3 here, even a simple methyl group, is getting really close to those hydrogens. So axials are bad. Because sterics suck. And it just true. So that's why it's not that, oh, I got a really good question in office hours. I never thought about this before, which is really awesome. That's why I love teaching this class. Where a student was saying, well, in this one conformation, we had these two equatorials, but they're adjacent to each other and they're gauche to each other, and that's bad, right? You want them anti. Yeah, you do. In any kind of Newman projection, you always want things, the biggest things anti if possible. But in those Newman projections, we're normally thinking about acyclic molecules not in a cycle, and so everything else can extend out away from each other. But in a cycle, everything's kind of twisted together and held tight, so you can't really ignore what else is going on. So what we're always trying to do with cyclic molecules is avoid axial groups. So our initial guess here, a 2-axial 3-equatorial looks promising, but we can't just rely on those numbers alone. We need to consider the relative size of the things that are axial and equatorial. In this case, a good clue and a good way to move forward is look for what the biggest thing is. How do you define the biggest thing? It is the thing with the biggest A value. Where do I go for the A value? I look up A value on Wikipedia and it's got the tables there. And we'll talk about A values in a second. That's how we're going to finish today's lecture. The thing with the biggest A value here, because it's the biggest thing, hopefully you'd realize the isopropyl group is bigger than everything else. And big is a bad word because big means so many different things. ISI, I'm going to come back to your question. It's a really good question. And you are talking about statistical mechanics. And I want to talk about statistical mechanics. And no one else in this class wants to talk about statistical mechanics. So we're going to talk about statistical mechanics, but we'll get there in a moment. Or maybe we'll get there next class. We'll see. So you want the biggest thing equatorial. That's our biggest thing. It's also, so the biggest thing being equatorial is also the one with the fewest axial things. This guy's our most stable. Check mark. It wins on both cases. Our total A value count's going to be lower. You can normally just take the biggest thing and run with that. 90% of the time, that's accurate. If you start seeing that I've really, like, there's like one thing that's slightly bigger than other things, and you know, there's two of them that are almost the same size, and both of them are axial, and you need to balance it. But here, big thing, everything else is quite a bit smaller. So that's our most stable. Then I said, let's do the Newman on that. And you're probably thinking, please don't make me do that. But I am going to make you do that. So we're looking down the 4-5 bond and the 1-2 bond. So if we look at where those are here, just delete a few things. So we're looking down that bond and that bond. So what we're going to do is we're going to contort ourselves into flatland as two-dimensional beings and move into the plane of the page, or what we could do is we rotate the chair and make our life a little bit easier and just look down this bond and this bond. Because, oh look, that's 1-2, and that's 4-5. And that's a whole lot easier to see. So if you're not sure, if you have trouble trying to draw a Newman from the projection you have, you can rotate your chair. So let's do that. So I'm going to draw my Newman over here. I draw 2 circles. Good enough for circles. I can hear you judging me. So carbon 1 is the carbon in front. Carbon 5 is the carbon in front. Yes, I know what this looks like, and no, I am choosing not to comment on that. Carbon 4 is the one in the back. Carbon, grow up. Carbon 2 is the one in the back. So between carbon 1 and 5, if I'm looking at carbon 1, 2 straight down, and we can draw in the hydrogen if it helps. I'll draw on the hydrogen in a different color. Green. There, that looks better. If I'm looking straight down the carbon 1,2 bond, I'm going to have a hydrogen pointing right down. In my right hand, I've got the rest of the ring. In my left hand, I have the isopropyl. Peeking out behind the circle of this bond, I asked you to draw the Newman based off the most stable chair. You can draw a Newman off the, so Madison asked, so our Newman is based off the most stable chair? Yes, because I asked us to do that. You can draw the Newman based off anything though. Like the Newman is a projection. You can draw any projection and you can project any structure you like. It's just if the question asks you to draw the most stable chair, then you use the most stable chair. So carbon 2 is behind. In my left hand, I'm going to have this fluorine sticking out and it's going to be kind of coming down below. In my right hand, I'm going to have the rest of the chair. So notice now I've kind of drawn the chair. There's 6 atoms there now in a chair. Like there's the front carbon, back carbon, back carbon. That's 4, 5, 6. And on carbon 2, pointing straight up is a hydrogen. Then on carbon 5, pointing straight down is the fluorine. My left hand had that rest of the chair. Now I'm shifting my view and I'm looking straight down 5, 4. My right hand has got a methyl group, the methyl group. Okay, something's weird about my electronics. And on the back carbon, left hand has the rest of the chair. Right hand has a hydrogen. And straight up is the ethyl group. So there, we've drawn the Newman projection of the most stable chair. So to do that, what we had to do was we had to number, either mentally or on paper. I did it on paper here, but you can do it mentally, it's fine. There's no marks for the numbers. Draw a chair, place the substituents on the chair, flip the chair, analyze the chairs for which one was more stable, determine which one was more stable, rotate it if you need to. If you don't need to, you don't need to rotate. You could have gotten this exact, I can draw this exact same in Newman projection by rotating my mind around this thing. I've been doing this a really long time. If you can't do that, rotate your chair. So again, and just make sure everything keeps going clockwise or counterclockwise. And I keep thinking that's a 1, and I go, no, it's all wrong. But no, this always goes clockwise. Then draw the Newman projection. You should be also able to practice unfolding these as well, going back from a Newman to the chair to the structure drawing. Because I think going forward like this is harder, but going back is equally important. We need to switch back and forth to these different projections. Why are we teaching all these projections? Is it just to torture you? It's not to torture you, but that's actually, it really isn't the primary reason. We're going to start talking a lot about reactivity, and it's very difficult to see reactivity from the structure line drawing occasionally because you need to see the relative positions of things. And you can do that from a chair, but sometimes it's easier to see it from a Newman projection. And so we are going to be going back and forth with those. Okay, let's do a double Newman projection back to, I don't have a model at home, that's the issue. And I can make a tetrahedron with my hands. I cannot make a chair with my hands. No, it's not wrong to flip the Newman projection. You're right, I lied. I flipped my Newman projection backwards. It's fine. I always say looking down the 4 or 5 bond or the 1-2 bond, but we'll accept the Newman projection out backwards. That's fine. Yeah, Samantha, you're right. I have it. I drew the eyes here. I meant I was sort of indicating, I'd probably indicate these bonds rather than the directionality. Because you need to rotate how it makes sense to you. Both are correct. You'll get this, you get exactly the same Newman projection. It's just backwards. But let's do one, okay? Let's go from a Newman projection to a chair. This is some fucked up over substituted chair. I don't know. Just someone got me thinking about phosphorus. I have no idea what I said, Fatima. I said this is a stupid chair. But anyways, what we're going to do is we're going to go backwards from a Newman to a chair. Okay. So what we want to do then is let's number our carbons. Carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. Let's start with numbering. Let's draw a chair. Now, we're going to make our life a lot easier if we make our life a lot easier. You can number this any way you like. You can go in any order you like. As far as I'm concerned, I have an easier time pretending I'm looking down these two bonds than any other two. Because these two kind of seem like the front of the molecule. Of course, I have drawn the wrong chair because I should not hit this very hard. I'm going to break my stylus. The problem was I had drawn the up part was. No, I drew the right chair. Oh, no, it doesn't matter. This is where I get confused always. Yeah, I can't look down those bonds because anyway, I've been drawing chairs. I have this up part at the front and we need the front to be down. So what's the best way I can, oh, you know what? Actually, I'm going to use this as an example to how to solve this problem because I want to look down, for example, these two bonds. The problem is I can't, because if I do that, this is up, this is down, that doesn't work. So what I can do is I can flip my Newman projection. I'm just going to rotate this. So what am I doing? Okay, so let's just draw the Newman. Now carbon 3 is in front. Carbon 6 is behind. Let's start with that. Carbon 2 is in front. Carbon 2 is in front. Carbon 1 is behind. Carbon 4 is in front. Carbon 5 is behind. So what I did is I took my hand, pretend your hand was Newman projection, and I did that. So the left became the right became the left, the front became the back became the front, because that's what flipping things does when we live in three-dimensional space. If it's in four-dimensional space, things are weirder. Again, really happy I'm not in four-dimensional space. Kind of like the phosphorus thing. Okay. So now if we do that, let's just start doing these one by one. So carbon 1 is in the back. All the ups remain up. So this methyl group, which was in the front going up, is still in the front going back going up. The ethyl group is now off to the right. It was to the left, it goes to the right. Carbon 2 had a phosphoric acid substituent attached to it. We don't need to worry about drawing it out. You could replace if that makes you uncomfortable, just replace it with a bromine. That's fine. It's for this, it's all the same, and actually would make more sense. This is not a stable molecule when I'm drawing, because that phosphoric acid is not going to be there. And then we're going to have a hydrogen off to the right. Carbon 3 and carbon 6 are really simple. We don't do anything to them. Carbon 4 was in the back. It has a fluorine pointing straight down. It had a methyl group pointing to the right, so it has a methyl group pointing to the left. And carbon 5 was in the front, and now it's in the back. There's my OH. There's my iodide. So what we've done is we've flipped the hand. You can, again, if you need to, you can do this with the model kit and build this and take a look at this. But now we have the right thing. So if this is carbon 4, and this is carbon 5, and this is carbon 2, and this is carbon 1, carbon 3 is up above them. So there's 3, there's 6. So everything is right. Now it's pretty straightforward. There's a axial fluorine. There's an equatorial methyl on 4. On 5, there is an axial OH, and it's axial up, and there's an equatorial iodide. On 1, which is in the back, there is an axial methyl group and an equatorial ethyl group. And on carbon 2, there is an axial phosphoric acid group and an equatorial hydrogen. And now if we want to complete the exercise, and we want to go back to a line drawing, all I need to do is I need to shift my view. So instead of looking at this isometrically, I'm now going to shift so I'm looking at it straight from above. And if I do that, let's keep our life easy by not having to rotate anything. So carbon 1 has an up methyl group and a down ethyl group. Try and do the rest of it. Today I'm drinking strawberry and kiwi Perrier juice. It is not as good as the cherry peach one. I grew up in the 90s, and strawberry kiwi passion fruit awareness was like the drink. And so I think I want this flavors to be a whole lot sweeter and a lot worse for me than this. Okay, hopefully you've had enough time to try and sketch things out. So the phosphate thing is on the bottom. On carbon, there's nothing on carbon 3. On carbon 4, the fluorine is on. The methyl group is on top of the fluorine. On carbon 5, the hydroxyl group is above the iodine. And so there, we're done. So I think it's easier going this way, with the caveat that I drew a difficult, I drew the hard Newman. That was unintentional, but still we got an exercise in 3D rotation. But the rest of it is pretty straightforward. Oh, what the hell do I know? It's straightforward for me, but I've been doing this a really long time, so that's a completely unfair statement. I would still practice doing this because we are going to be doing Newman projections for stuff, so I'm going to switch over back and forth between these projections later in the course, as a matter of course. So you do need to be kind of at least not terrified like deer in headlights with the projections. Sorry, how come the methyl group on carbon 4 is not a dashed line? Okay, so there's a carbon 4 has an up and down position. The fluorine is below, like it's down. So the fluorine has to be the dashed line. The methyl group is up, it's coming out of the plane because the fluorine is going into the plane. So if you're having trouble seeing that the methyl group is up, think rather that the fluorine is down. So if the fluorine is down, the methyl group must be up. Yeah, the equatorials are hard. If you're ever kind of confused about an equatorial, whether it's up or down, draw in the axial, and there's no question about whether an axial is up or down. That's super clear. So the equatorials are all up or down relative to the axial. This Newman down here? Yes. No, I have it right. Because remember, carbon 3 was in the back here. Now it's in the front. I'm just rotating. All my ups are up, all my downs are down. So like if I rotate my cell phone case, my camera right now is facing towards you, but it's on the top of my cell phone. If I rotate it, my camera is now facing away from you, but still on the top of my cell phone. Just start here if you want to go through without flipping Newman. Will I have office hours during reading week? I think officially it's reading week, so I don't. But if somebody wants to arrange, if I get a few emails saying, hey, I'm going to show up at Tuesday at 9 a.m., I will be there. That's fair. Why do we have to flip it? Because either way that we've been drawing chairs, notice that the carbon closest to us in the middle here, if we're looking down this bond or that bond, the carbon closest to us is above these two. The problem we had was that on these front carbons, the carbon there is below those two. And if I want to look down these bonds, which I really do because they're easier to do, I'm screwed. Like in both cases, that carbon in between is above the base, and here it's below. So there's nothing wrong. You can do this if you want to look at these chairs from a different angle. Like if I want to look down, this bond and this bond. It's just that's a little bit harder I find that harder to do. Because now I have to rotate my head. In general, I suggest until you're really, I can do it pretty easily, but what I want to say is because I'm really used to doing this, until you're really good at rotating this stuff in your mind, rotate stuff on paper. Do it step by step on paper. Don't try and do these rotations in your mind. You will screw yourself up. I guarantee it. Once you get really practiced at it, go nuts. Are you going to be really practiced at it in this course? If you have a sense of being able to, if you are just really good at three-dimensional rotation and three-dimensional thinking, you might be. If you're not, keep doing it on paper. I do. This is what office hours are. Like the whole idea is I answer questions. It's really basically an extra class. It's just I think there's like 4 people in it and they get their specific things answered. So that's why I'm gonna when the office hour questions are not logistical, if they're course content, I'm recording them and throwing them up there too, so you kind of get like a 4th class. It's more like problems. Would it be bad to look at carbons 1 and 5? Well, you can't look down the bond between carbons 1. Oh, if I flipped it backwards. Yeah, that's fine. No, that's perfectly fine. That's what we did up here. It's just I couldn't draw this using this chair by looking down these two bonds. It just doesn't work. That this is down in the front and it's up in the front and it just office hours are there every week. And Samra also takes over from me right now or in 5 minutes. I don't know if she needs to pop out and take a bio break or something, so I'll keep talking. But yeah, my portion of this is done. I think I've covered the questions I want to cover. I got a really good question about hyperconjugation. It was a great question. I will put up the SciComm. I will put up SciComm examples and rubric next week. I'm going to make sure I'm using my time when I'm not teaching to do a little bit of that. So you can get some examples. It doesn't. So either one is right, Melissa. So you can draw either Newman. It would have been either one of these. If I'd asked you to draw Newman down the 1-2 and the 5-4 bond, you drawn either one of those, full marks. You don't need to do both. Samara, sorry, I'm at home, so I can't lend you my stylus. So you might need to do this by interpretive dance. Or maybe you move this thing to Friday. Yeah, you can put any orientation for the Newman as long as it's right. I will often say which bonds I want you to use. And so if you don't put that bond in your Newman, then you're not doing what I told you to. But if you flip it backwards, that's fine. Oh, okay. So as long as the bond I say that you need to be looking at is in your Newman projection, like is being drawn as a Newman, then it doesn't matter which way around you're doing it. It's the same thing. The GAs can rotate things. And if they can't, they're going to get good at it. You are allowed to torture the GAs gently as well. Yeah, so next class, we are going to start discussing stereochemistry, RNS and naming that, and that's why I've been so anal about the wedges and dashes and stuff. And then there will be an assignment going live Thursday night, midnight. If I told you to go from this to the Newman, I'd probably say, so the question was, if we went backwards, which bonds are we looking at? I probably would have like circled these two. I said the 5-4 bond and the 1-2 bond. But you could have looked down 2-1 and 4-5 like we did, or you could have done it backwards. Both those would have been fine. I'm sure if I drew it this way, though, 90% of you would do it this way. Up to today's lectures on the assignment. So up to, I guess, chairs and rings. So conformations, acid-base equilibria, charge stability. We're not going to actually evaluate. We use specifically on stuff that was evaluated on assignment 1, but everything you learned on assignment 1, we've scaffolded on top of that, right? Like, it's not like we abandoned that. It's not like the module finished and like we stopped talking about fish. Now we're talking about toads. All this stuff builds together. it is likely to be multiple choice again. It depends how excited Samra gets with the question answer options available to us. We haven't talked about hyperconjugation yet. I've decided I want to spend quite a bit of time discussing that. You can read about it. Some of the lectures discuss that I've lectured on it, discuss it, but it's not. It hasn't been relevant for our stuff yet. So you come across a question, talk about hyperconjugation. You can ignore it for now. Yes, the assignment is Friday, Saturday, so it goes live Thursday Thursday 11:59 or Friday 12:01 a.m. or whatever. Oh God, yes. I think so, Sarah. I will. Yeah, practice assignment 1. I will go through that again and just make sure that's all relevant, and then for some of the other ones as well. It's hard to ask questions about all this stuff, to be honest. It gets a lot easier in the second half of the course for me to ask questions, not for you to answer them. But I'm a narcissist, so I don't really worry about what other people think. But yeah, no, I think it's assignment 1 and assignment X, and if there might be assignment 0, because I kept doing earlier. No, the assignments are harder than the midterms. Oh God, the assignments are harder than the midterms. Oh, these these Thursday, Friday assignments. Yeah, those are probably, well, they're multiple choice and the midterm's not multiple choice. I don't know if it's harder or easier. But the assignments I posted. Yeah, no, those 4 assignments, those are going to be. They're multiple choice and the midterms are not multiple choice. So is that harder or easier? I don't know. You're going to draw stuff on midterms. It's just really, the computers are stupid, and so we can't teach them to mark drawings. The midterms are marked by people. Yes, I will confirm that, Madison. I will be yes, for sure. I'm going to confirm exactly which questions are relevant. It's probably all of them, because I haven't reorganized this that much this year. And then it might be parts of assignment 2, though I need to confirm. If there's an assignment 0 as part of that too. I can't remember if there is. I just have to take another look at those because I haven't looked at them in a while. The answer keys are all up there too, right? So, okay. Good luck. Happy studying. Over to you, Samra. Sarah, I'm not 100% sure. The lectures, the spoken lectures are a little bit later on those from previous years. I think I talked about reaction coordinate diagrams a little bit later in the course, but they're there. Okay. Bye, guys.
Hi guys, hello everyone. So I'm gonna go and I guess stop the recording and wait